the whole thing was based around the first law of thermo, right? Which says the rate of change of energy in a system is a matter of bookkeeping. How much energy goes in the form of thermal energy, heat transfer, and how much energy comes out of the system in the form of mechanical work. We went through, we said system conservation laws, right? We've spent the whole chapter turning those into control volume conservation laws. Same thing applied here. And so by going through those steps of saying what is the extensive energy or extensive property of the system is energy, the intensive property is the specific energy, the energy per unit mass, applying the Reynolds transport theorem, we ended up with multiple forms of the energy equation. So I'll put this slide up on icon so you have a nice summary slide. I've also written up kind of the most important versions of this up here, so we can come back and reference this as we're working through examples. Right, we've got the energy equation in its full glory at the top. If you say that the enthalpy, right, this H hat, is equal to the pressure over rho plus the internal energy U, then you can write this in terms of enthalpy. So the second version of the equation, right here, is the one that's more often used for compressible flow because enthalpy is something you can get out of like the steam tables, right? If you are able to assume that the flow is incompressible, then you can get rid of those parentheses around the P over rho, okay, because rho no longer changes at the inlet versus at the outlet, and you can start to write this in forms that look more like equations we're familiar with. So this first version of the energy equation, the only thing that's happened is we've gotten rid of these parentheses. Then if we go ahead and divide through by m dot, okay, the mass flow rate, we end up with this version right here, which is also known as the extended Bernoulli equation. And it looks just like the Bernoulli equation that we have P v squared over 2 G Z at some point we call the outlet, some point we call the inlet. You could say 1 and 2 instead. The only difference between this and the Bernoulli equation is, of course, that now we've said there's something causing losses in the system, right? If P, V squared, and the elevation all are basically forms of energy per unit mass, that loss represents, right, dissipation of that energy to heat, to thermal energy. So it accounts for the change in that up at the top on the right there. Loss is the change in internal energy caused by a rise in temperature, okay, minus the amount of heat transfer that's been added to the system. And then finally, if we divide this whole thing by G, we end up with the energy head equation, which puts everything, it's exactly equivalent to the two above it, but this one has units of, or dimensions of length. Okay? So every term in here represents, for example, the equivalent height of an item that had the same potential energy as that term has in whatever respective type of energy it is. All right, so enough elucidating on the energy equation. Let's start putting it into practice. So the format here is I'm going to go ahead and give you guys a problem. We're going to give you about 5 minutes to get a start on it. And then I'll have you, right, if you get stuck, you are welcome to turn to whoever's sitting next to you. You can work in pairs. But just spend the first 5 minutes getting as far through this problem as you can. If you're able to solve it, great. Check your solution with me at the end. And then we'll go through as a class and we'll answer any problems or address any difficulties people have had. So getting started on this, the first step is to pick the form of the energy equation that you're going to use. All right, so looking at these equations up here, which of those lends itself most easily to this particular problem? let's take a pause here for a second. I guess show of hands here. How many of you are like on track to a solution? All right. So take the next minute. I'm going to turn to whoever's sitting next to you and explain like where you're at in the problem and compare your progress so far and like how you plan to proceed. And then we'll spend another couple of minutes with it. All right, let's regroup. So at this point, let's switch over here. Which form of the energy equation has the sort of your consensus decided we should start from? If we number these from 1 to 4, going from the top to bottom, anyone in favor of using the very first one, top, second, third, fourth? All right. Those for the third and fourth, you're both, actually second, third, and fourth, you're all correct, right? Because these are all exactly equivalent. Probably the one that requires the least work on our part would be the fourth one here, because we're given a head loss, right, in meters. We're given an elevation change, so we know Z1, Z2. We know P1, P2, because they're both atmospheric at both points in the pool, right? And so just in the interest of saving ourselves some pencil lead, we might start from, right, the head equation. So writing P2 over gamma. Here, let me zoom in here. There we go. P2 over gamma plus V2 squared over 2G plus Z2 is equal to P1 over gamma plus V1 squared over 2G plus Z1 minus HL plus HS. All right, so looking at this problem, what terms can we immediately get rid of? About P2 and P1, right? If both points on our, we said that 2 is down or up here and 1 is down here, right? Both are open to the atmosphere. So the same pressure, so we can cancel those guys out. We're assuming these are, right, large reservoirs. There's no indication of any sort of overwhelming velocities in either of these pools, so we could go ahead and approximate V1 and V2 as being 0. And so what we've got at this point now is, right, a change in elevation, Z2, Z1, that's obvious. That's given in the problem, it's 10 meters. Head loss, which is given, and so there's only one unknown, and that's the shaft head, this H sub S. And, right, this H sub S now involves, right, it involves our shaft work. This is one of the things we're looking for, right, this W dot S. And we already know what that shaft work is at 50 kilowatts. And so by comparing our shaft head, H sub s, with the known W dot sub s, we'll be able to get M dot times G, right, which is going to allow us to get Q. So the next step here would be solving for the shaft head, okay, H sub s, which is simply going to be, right, Z2 minus Z1 plus the head loss. 10 meters plus that 4 meter head loss is equal to 14 meters. Thinking about this a little bit more abstractly, right, what this is saying is that the pump, right, this H sub s is coming from the pump. That pump has to supply enough energy to the flow to elevate it that 10 meters and overcome the losses for that 4 meters of head loss. So if H sub s is equal to U sub s over M dot times G, we could also write this as W sub s over Q times gamma, right? Which means that you solve for the shaft head or the shaft work rate. Sorry, we're solving for Q. We know that shaft work rate is equal to 50 kilowatts, okay, because that's the pump power that we are given in the statement for the problem. So Q can be solved for then as S divided by HS times gamma. 50,000 Newton meters per second, right? Because that's a watt, divided by that shaft head of 14 meters times 9810 Newton per meter cubed. This should give us a value of 0.364 cubic meters per second. All right, so now that we've got that, I'm going to leave you guys for another 2 minutes to try to work out what the rate of energy loss is. Okay, the rate of power or of energy dissipation. So I mean, to think about it, this one doesn't have an equation written up here, but right, if loss there represents the amount of energy loss, if the head loss, okay, is 4 meters, compare that to how we I guess the head loss and the shaft head, right, are equivalent in kind of the type of terms they are. They're both given in meters. But think about how we got a power, right, a rate of energy transfer from the shaft head. Apply the same thing to the head loss and see if you get a rate of energy loss. So it would take it about a minute to see if we can get a number out of that. Right, if the head loss is 4 meters, given in the problem. Seems about right. So if we said that the rate of power loss, I get about 14.3 kilowatts. Okay. Ways of getting this, same thing, right? We're solving for the rate of energy loss. We know H sub L is equal to 4 meters. Take that, multiply it by gamma times Q. You should get that number. Another way you could do it, all right? If H sub L, okay, the head loss, represents the potential energy equivalent of that lost energy, and H sub S, the shaft head, okay, represents the potential energy of the work per unit mass being, or the energy per unit mass being injected into the flow by the pump. The idea is here that H sub L over H sub S should be equivalent to, right, the power loss over the shaft power. Okay? So you can solve for it that way too. You can say that 4 meters over 14 meters, okay, is the same as the ratio of the power loss to the shaft power. So 4 over 14 ends up being, what, just a little less than a third. If the shaft power is 50 kilowatts, a little less than a third of that should give us our 14.3. Okay, so two ways to the same solution there. Okay, next problem. Consider a case where we've got a turbine now, rather than a pump. Remember, turbines and pumps look the same, but one has a positive sign, one has a negative sign. Injecting energy versus extracting energy from the flow. Okay, so we've got superheated steam entering a section 1, regular old, just heated steam. Leaving it section 2, we're assuming the flow is adiabatic, steady in the mean, and that it remains at a constant elevation. And what we're asking to find is the work extracted through this turbine per unit mass of flow flowing through it. So, right, if the work per unit mass is, right, W dot S over M dot equals this little W right there. Okay, my second term. Sorry to take a few minutes here, and then same thing. We'll do a little bit of pairing off, comparing notes, and then come back to the solution as a group. next minute, same thing. Turn to whoever's next to you and compare notes and roadblocks. All right, and let's regroup again. So this one is right. This one we'll step through in a little bit more orderly of a fashion. I'll go ahead and lay out the steps that I would use to solve this. All right. Step number 1, said before, is pick the form of the energy equation that you're going to start from. So again, poll by show of hands. First equation. Okay. Second equation. Third. Fourth. Good. Right. And what's the major consideration here? Anyone want to volunteer a reason they picked the first? Heard somebody say compressible, and right, you're given enthalpy. That's the other big thing. Yeah. You're given H hat at both the inlet and at the outlet, right? What's the problem with using the first equation? Not that it's a problem, but what's the what don't we have written out in this version of the equation right here at the top? Okay. What are we looking for? Okay, it's the shaft work per unit mass. Is that equivalent to our W dot shaft term on the left-hand side? No. How can we make it equivalent? Just divide that whole equation through by m dot, right? And that's going to give us now the energy per unit mass. So let's go ahead and proceed with that. So starting from the energy equation with enthalpy, right? Q in plus Qs in is equal to m dot V2 squared minus V1 squared over 2 plus G Z2 minus Z1 plus H2 minus H1. Right. From any of these givens, can we, at this point, can we cancel anything out immediately? That can go away, right? What about Q dot in? Right? Because we've been told that it's an adiabatic flow, so that's 0. That's 0. And then we just established, right, that to get this form of the equation in terms of the variables we want, we would divide through by m dot, right? So that'll get us so I guess that right there would have really constituted our step number 2, which is state assumptions and simplify. So assume and simplify. And then step 3 would be populate equation, solve for our unknowns. In this case, we have a very straightforward case because we know V2, we know V1, we know H2, we know H1. So our only unknown is already isolated on the left-hand side by itself. Okay? So if we just plug in values, S in is equal to V2 was given as what? That one was 60 meters per second, right? 60 meters per second squared minus 30 meters per second squared over 2 plus 2250 kilojoules per kilogram minus 3348 kilojoules per kilogram.
So we need work shaft divided by mass flow.
This has already been divided by a mass flow rate, right? If we take this W dot shaft, right, and we divided it by M dot,
Right.
then we end up with this term right here, right? That is the shaft work per.
Alright.
So if W dot is right rate of shaft work, and we divide it by rate of mass flowing through it, okay, you sort of can do some word algebra here, and you end up with cancel out those rates of, and you end up with shaft work per mass. And so if you plug these numbers in, you should end up with negative 796.7 kilojoules per kilogram. Okay. What's that negative sign indicate? All right. The work is coming out of the system, right? We've signed this as positive for work going in. Negative means it's work coming out. So, right, we could say here that the turbine extracts 796.7 kilojoules per kilogram of steam that flows through it. Okay. Now this one's a little bit unusual for the cases we've been, or for the in comparison to the equations we've been solving and the cases we've been looking at, because this is, like I said, this is a compressible flow. We're dealing with clearly flows at very different temperatures with very different densities, okay, going in and out. That's the way that steam turbines work, right? But because if we knew the temperature, we knew the pressure, right, we could use the steam tables to look up that enthalpy number at the inlet and that enthalpy number at the outlet. I see a couple hands. Yes.
Is that value calculated correct?
I think so. Is it people not getting this?
They just have to convert from kilojoule to joule to work.
Oh, it's just joules per kilogram, you're saying? Or?
You're like multiply by 10 to convert to joule for it to get this number. 2250 times 10 to the third.
Kilojoules per kilogram? So I'm just missing a factor of 1,000.
No, you got the right answer. You got the right answer.
Oh.
You have to take the first term is in joules, the last term kilojoules. So you have to divide the first term by 1,000. 2,000.
I guess I'm. Oh, divide. Oh, okay. Well, you're saying that this guy has a factor of 1,000 in there? Okay. I guess I'm. Well, okay. Yes. For if you're just dialing in numbers, yes. but if you recognize the units here, that should be correct as it is. Okay. So we'll say joules per kilojoule there. All right. Were there any other questions on this one? I saw a couple hands go. That's just, yeah.
I guess I'm kind of confused on the units too. So meters squared per second squared is equivalent to kilojoules per kilogram.
It is. Yeah. Yep.
I got a completely different number. Like I converted meters per second to kilojoules per kilogram, and then I added the other stuff. I got 1,096. Like after you multiply by -1, there's like 1,096 joules per kilogram. Kilojoules per kilogram.
You plugged in
Is it-
250.
I did 2.55.
Oh, is it supposed to be? Did I write that wrong? I did. I'm sorry. There we go. That's supposed to be 2550. That 300 factor, 300 or around 300 should account for the difference between 796 and 1096. Sorry. Okay. We good now? We're all happy? All right. Let's look at another one. This one's a little bit more involved, and we will probably run out of time on this, but I've got the solution ready to post to Icon so you guys can go back and check it. So this is a two-part problem, right? It's going to make you go all the way back to chapter 2 to look at some manometry. But I would solve this in 2 steps, right? The first would be to find the pressure difference between points 1 and 2. Okay? And then once you have that pressure difference, go back and solve for, right, do the manometry problem totally separately. Okay? So we can go ahead and, for this one, we could go ahead and say that gamma, right, water is 9.81 kilonewtons per meter cubed, which means that rho water is equal to 1,000 kilograms per meter cubed. Pause here, make sure we're on the same page. So as before, it behooves us to pick out our form of the energy equation in a way that's going to save us some work. So we'll go ahead and recognize, right, it's water, it's incompressible. Let's assume we're not using the first one that has enthalpy. So which of the 3 here, as show of hands, how many picked the third one, the head equation? Okay. What about the middle one, second one? First one? How many people did pick the one at the very top? Okay. There's a lot of people that haven't picked an energy equation. So again, anything here will work. Clearly, we've got some different things going for these different forms of the energy equation, right? Let me bring this down here so we've been given, right? We've been given the shaft work, right? The pump power. So we've been given this quantity. For example, if we want to make this the, we've also been given the head loss. Okay, so we sort of have a mixture of knowns here. Again, I like to start from, especially when you're given a head loss, I like to start from the head equation. Okay. So if we start from the head equation, we end up with, if we took the head equation and we reorganized it a little bit, I'm going to go ahead and save us some time and say the head equation P2 minus P1 over gamma is equal to V1 squared minus V2 squared over 2G plus Z1 minus Z2 plus HS minus HL. Okay, so I've taken the head equation and I've reorganized it a little bit because, like I said, our objective would be first to find P2, P1. So identifying our unknowns here, right? We don't yet know V1, V2, HS, or HL. We know Z1 and Z2, right? Being that the 1.5 meters. Or we know HL too, because HL is given to us as 2.5 meters, right? We could find H sub S in this equation right here. Divided by, we could say Q dot rho dot G would be 6 kilowatts over 0.065 meters cubed per second times 9.81 kilonewtons per meter cubed. And this would work out to a value of 9.41 meters. And we are about out of time, but I will post the annotated solution to this one on Icon so you guys can check your progress against it. And see you guys on Wednesday.